Howdy there. In the last video, we looked at some basic market statistics, looking at the daily returns of the S&P 500 index. We calculated things like mean, standard deviation, skewness, kurtosis, things like that. And during that video, I plotted out a histogram of the daily returns and noted that it wasn't a probability density as I had plotted it, and that we could make it so by using a flag in the matplotlib library, density equals true. So I figured I'd go back and explain what I meant by that and show how to calculate it if you didn't have that type of flag in your function, like I don't believe MATLAB does by default. So how to calculate that, and then I also thought it would be interesting to try to actually pull from that distribution. So if we wanted to use the actual historical returns instead of like a normal distribution, how could you sample from that historical distribution in some way if you want to do, for example, Monte Carlo simulations or tweak some sort of options models? How would you actually go about doing that? So that's more or less what we're going to do here. This video ended up being a bit disjointed because it was actually made over a period of several days and things kept coming up. There was traffic, they were doing traffic work outside when I was trying to record. And so if it is a little more disjointed than usual, I apologize for that. But yeah, let's get on with it. So this is the notebook from last time where we calculated things like the mean and skewness and kurtosis. And I generated this histogram here, and I made a comment originally that it was not a probability density and that we could turn it into one by using this density equals true function here. So by default it's set to false, and you get a histogram like this. So I didn't really go into a lot of detail as to what that exactly is doing. I mentioned that it basically rescales it by the area under the curve, but I thought I would go through and talk about this in a little more detail. And I also thought it would be fun just to play around with this a little bit. And for example, say we wanted to do a Monte Carlo simulation using actual stock market data rather than a normal distribution that the Black-Scholes model assumes. So how do we go about doing that? How do we sample numbers perhaps from this this histogram rather than from built-in SciPy normal distribution functions? And so obviously that depends a little bit on how you build this histogram, how you do the binning and whatnot. But I'm just going to keep it basically as I have here. I think this is 50 bins. Where's my function? Where's my function? This is 100 bits. Maybe I'll do 50 or 100. We'll see. But we'll just take basically what we have here and show how to sample from this histogram. Now there are a variety of ways to do that. We're just going to do something very simple. It's been done. I think they started doing this in the early 1800s. In fact, it's probably the simplest approach you could take. So let's get on with it, and we'll set things up in a new notebook actually to begin with. So okay, over here in a new notebook, these will be our imports. These are the same things we've always been using recently. NumPy, a couple things from SciPy, Matplotlib, and we'll use pandas to pull in the SPX data. So let's just run these and make sure they come in okay. Cool. Let's just start off with something that's easy. We'll just start off with the normal distribution. So NumPy has the ability to sample directly from the normal distribution, and the function is in the module random. And did I spell that right? It looks like I did. And the function is called normal. And you can specify the mean and standard deviation, but if you leave them blank, it comes back as 0 mean and 1 standard deviation. And you can specify the size. So let's just make this, I don't know, 10,000 points. Let's see if that runs. Does help to have an equal sign in there. So we'll just call these this variable samples, and that looks good. So let's just take the mean and standard deviation and see if we get what we'd expect. So np dot mean samples looks good, close to 0. Let's just put a print statement. Print mean equals that, and we'll do the same thing for standard deviation. Print std is equal to np.std samples. So it looks like this didn't automatically close itself off. Come on. Boom. There we go. So mean close to 0, standard deviation close to 1. So let's actually just bump this up to 50,000 and see what we get. Roughly the same thing. So I plotted the histogram here off camera and off of the recording. And this histogram function, I believe I talked about this in the previous video, it returns three variables. Counts, which is the count in each of these rectangular bins. Bins, which gives the coordinates, the x coordinates of each bin edge, and a variable called patches, which contains the objects used to draw, these rectangles used to draw out the histogram. So if I wanted to go in and change a color of a specific one, say to red, I could do that, or I could adjust it, or get some information about it off of that. So I just passed in these samples, our data, into the histogram function. I set the bins to 50, and I also use this edge color equals black. Otherwise, it doesn't draw these black rectangles, and it's kind of hard to see what's going on. So this looks basically like a standard bell curve, but in the previous video, I said this is not a probability density. And if you recall, if you integrate a probability density over all of the all space over all the x values, the area under the curve should come to 1. So let's actually just plot out what a regular normal distribution would look like, and we'll just numerically calculate the integral just to see that that's the case. So let's come down here, and we'll say x is equal to np dot linspace, and we'll go from, I don't know, -5 to 5, and for the time being we'll do 100. Let's do 1,000 points, and then we'll cut it down later. So y is going to be equal to np dot, it's not np, it's norm dot pdf, probability density function, and we're just going to, what are we going to do? Pass in our x values. And if we leave the mean and standard deviation out, again, it takes it to be mean 0, standard deviation to 1. So that runs, and just let's just plot that out. So plt.plot x comma y, and we will use a black line. So there's our plot of a normal distribution. You see the peak only goes up to like about 0.4 here, and this obviously goes up to several thousand. And if I were to adjust this, even let's add a factor of 10 to this, to the number of points here. I should pay attention to what's happening on the screen here. I deleted the number and replaced it with 0, so it was 50,000. If we add a factor of 10 to it, so it's now 500,000. Let's rerun all this stuff. You see you have more data points. Obviously, you have more points, you're going to have a higher curve. So obviously, the area under this is not equal to 1. And so how can we deal with that? Now I'm going to show two ways to turn this into a density function. And the easy way with this particular plotting package, matplotlib, is you can just add an argument here, density is equal to true. And that will do the rescaling for you. In fact, let me just cut this out here. Cut. And we'll overlay it on the same plot here. So here, let's go to the end of the line. Plot it. So you see that lies on top of it almost perfectly, which is you'd expect. But the issue is sometimes you can't do this. Your plotting package doesn't have this ability. I don't know if MATLAB does or doesn't, but I'm going to show another way how to do this manually using these counts and bins arguments here and patches. So I'm just going to copy this whole line out here and go down. Where do I want to go? Let's go down here. Paste it in here, and I'm going to change this to false so we can get back to our original histogram. So false. Okay, so in order to normalize by this total area, we need to know what that area is. Fortunately, these are rectangles, so it's pretty trivial to find the area of each of these rectangles, and then the total area, of course, is just the sum of all of those little areas. So let's do that. Okay, so the bins variable here contains the positions of all these bin edges, the x position of all these bin edges. So the width of the bins we could calculate as a vector, and we could go, let's call them bin width is equal to np.diff of this. So it's just going to subtract, it's going to calculate the difference between each of these data points, and that will be our bin width. So let's just print out this bin widths. And I think these are all uniform, so these numbers should be the same, and they are excellent. So let's get rid of that. And then the next thing we need to know is the height, right? The area of a little rectangle is the height times the width. So let's calculate the height. Well, that's just the counts, right? This counts variable here. Oh man, I cannot type tonight. Counts. For example, this is a 2. It doesn't show up on the scale, but this is just the first rectangle on the left has a height of 2, and so on. So we should just be able to multiply this through and get the vector that has all of the areas. So let's do that. Let's get rid of. How do I want to do this? I'll just do the whole thing in one line. Area is equal to np.sum. And we want to multiply those two vectors together, element wise. So it's np.multiply counts, and then we want to multiply times bin width. If I sound distracted, it's because they're doing construction right outside my window here, and the window's open since it's finally turned into summer here in Los Angeles, and it's whatever they're doing is making this obnoxious whistling sound. I hope it doesn't come in on the audio. So what did I do wrong here? Oh, np.multiply parentheses, that should do it, and p.multiply. Cool. So now we need to go through and divide each of these rectangles, each of these heights by that area to scale everything down. So I'm going to do that with a for loop, and we're just going to use the fact that this patches, where's this patches variable? Patches variable here is a list of rectangles. So for every rectangle in patches, we're going to get the current height. We're going to take the new height. The new height is going to be the current height divided by area, and then we're going to change it down here. So let's just run this. And nothing. Yeah, it helps to do it in the same cell, doesn't it? Come on, Kevin. Cut. Paste. So in principle, this should drop down and look exactly like this with a height of about 0.4. So let's hope that this works. Okay, and now we need to actually change the limits on the graph. So come down here, plt.y, plt.y, that whistling sound is really obnoxious. Ylim, go from 0 to 0.5. Yay, so that looks pretty much the same. Let's, what do you think this graph goes to? 0.42? Maybe we'll change this to 0.42. So that, yeah, there we go. Let's actually overlay the that normal distribution on here. So plot plt.plot x comma y, make it black. Yeah, it's identical. So if your software doesn't have the ability to do it automatically, that's how you would do it programmatically. It's relatively straightforward. Okay, so let's move on to the next part, which is how do we sample from a distribution if we don't have these built-in functions like we have for the normal? So I'm going to set that up, and I'm going to shut off the recording and add some figures to that to the screen before we move on. And we'll start off using the normal distribution just because we already have the functions built in to check our work, check our intuition, and then after that we'll move on to the actual XPX data. So with that said, let's get going. Okay, so I've added this little brief digression into cumulative distribution functions which we're gonna use to set up our sampling algorithm. So if you have a density function, it's pretty obvious that the probability of being between two values, say a and b, is the integral of that function between those two bounds. So if we're to take the probability density and integrate between minus infinity to x, This is what's referred to as the cumulative distribution function. And for the normal distribution, you can actually calculate this out. You get something that looks like this. And now this is a built-in function in NumPy and all sorts of software packages. So you could just plug directly into that. But for example, if I wanted to know what the probability of some value randomly chosen here being between minus infinity and 1, just pick an arbitrary number, you could do this integral here, and that's kind of shown here. The probability is equal to this area here, which is some value. Or if you knew this function here, you could just plug 1 into it and get out the answer right away. Let's quickly do that actually, just numerically before moving on to sampling. So I'm going to come down here and create a variable called u, just so that we don't use variables we've already used, and do linspace. I'm going to go -5 to 1 because this density function here drops off exponentially fast, so it's effectively 0 at 5 or close to it. You could choose another value if you want, but I'm just going to choose 5, and I'm going to do 1,000 points here. And then I'm going to create another variable v, and that is going to be equal to norm.pdf of x. Okay, so let's come down here, and let's right below here, let's actually calculate out the integral between -5 and x. And so -5 is our substitute for minus infinity here. So print trap z, np.trapz, which does a trapezoidal method integral, a trapezoidal algorithm to approximate an integral, v comma u. So that's our number, and now let's actually plug that into the cumulative distribution function and see what we get. So actually that number doesn't look exactly right. Something seems a bit fishy here. What's going on? Oh, I see. I put an x here instead of a u. That kind of makes a difference. 0.8. That sounds like a much better number. So let's come down here and do print. The cumulative distribution function is called norm.cdf. And let's pass in our value of 1. And we get pretty much the exact same thing except for like rounding errors. So, all right, let's think about how we could use this to sample from this distribution. If we were to pick random numbers, let's just pick a number between 0 and 1. And let's just choose for this convenient, we pick this number like we pick a number close to 0.84. So we come up here in 0.84 and we go over to the function here. Where's 0.84? Roughly right about there. This corresponds to the integral between minus infinity and wherever this intersects this line. So this gives us a way to map numbers between 0 to 1 to points on this line. So if it were 0.84 and we were to come over here and go across, we'd get 0.84 here, and that would correspond to 1, which we just kind of worked out. So if we go over here, it picks off this point on the distribution. So that's how we're going to actually set this up. So let's do that now. So actually, we're going to have to calculate the inverse of this function, and SciPy comes with a built-in tool to do that. The function, strangely enough, is named ppf. So if we were to take print norm.ppf and plug in this number here, we should get back 1, or close to 1 since it's a rounded number. Oh, we get exactly 1. Cool. So when we do the SPX data, we're going to have to construct our own way of inverting this, which is not hard, but I just thought I'd mention it up front. So let's calculate a bunch of random numbers between 0 and 1. So let's come down here, and we'll use the variable u again, and we're going to set u is equal to np.random.rand, and we'll just take 10,000 points between 0 and 1. Technically, this is the half open interval between 0 and 1, with 0 being included. This 1 technically is not in this interval, but we're just going to ignore that now because the probability of getting 1 is way out here in the distribution anyways, and I'm just lazy. So, okay. And now let's use a v again, and that will be norm.ppf of u. Let's just see if that runs. Excellent. So let's come down here and do count bins and patches. Patches. And that's equal to plt.hist. Let's see how this actually looks now. plt.hist, v, we're going to set bins equal to 50. We're going to set density equal to true. And we are going to set edge color equal to black. What did I do wrong here? I see. Yay, and let's just plot the actual, let's just plot plt.plot u, comma, norm.pdf of u, and let's make that black and see how that looks. Okay, since this is becoming a little on the long side, I already pulled in the SPX data, just the pandas data frame. I calculated the daily percent changed and pulled out into a numpy vector the daily percent change as its own variable. And we can just do the histogram here as we did before. So I have 100 bins, density equals true, edge color equals black, and here we go. I've also chopped down the x-axis because there's edit from the future. I forgot to turn on the recording for this part, and it was where I turned this more typical density into a cumulative distribution function. Unfortunately, matplotlib has the ability to do that automatically just by adding the option cumulative is equal to true. Yeah, there we go. I'm not going to take the time, since this is going really long as it is, how to calculate this. If your software can't do this automatically, but it should be pretty obvious. It's very similar to what we did earlier with what we did up here, rescaling things. So, okay, cool. Let's move on back to the normal video. I suspect there's going to be a small issue with this, in so much as this function has to be monotomically increasing. If you have functions that are the same value or it changes direction, you're going to have multiple points where you cut across. Like up top here, if you chose a 1, where on this exactly does your point lie? So that needs to be looked at. One quick way to check is just to print out the difference of the counts vector. So print np.diff count. Did I call it count or counts? Count. And you notice a bunch of these are zeros, and there's some zeros here, and then it goes from a positive to 0, so it changes direction and then goes back to a positive. So that's not good. So we need to address that just by tweaking the binning a little bit. And I'm going to try to come up with something off of the recording, and we'll go from there. So I'm just going to do manual binning, and I've set up a vector here called b, and then I set the bins equal to b. So if we rerun this cell, we get a histogram that kind of looks like this. What's going on here? I probably just left the scale the same. On another sheet I worked this out. So that's what it actually looks like if you include all the data. And now I'm just kind of scaling it down just for plotting purposes here. And now if we do the diff, you can see we have a bunch of unique values. So the diff is never 0. So let's just get rid of this here, and we will move on. And I think what I'm going to do is just do a linear interpolation. I'm going to take the center of the bins to be my x data, and then the counts to be the y data. And just like before, I'm going to use a loop to get the height of these bins. So, or the x coordinates of the bins, and work out their midpoint. So u I'm going to set to an empty array, and I will do for I. Oops, I'm used to MATLAB. For I in range bin.size -1. Let's just see if we're indexing this correctly. Print I. What's going on here? Oh, my bin vector is already defined as b, so b. Okay, so that's working. And we want to append to U the midpoint between each bin. So U dot append B I plus 1. I'm going to want this all in parentheses. So B I plus 1 plus B sub I, close parenthesis, divided by 2. Close parenthesis. Okay, that looks good. Let's see if it runs. Good. And before moving on, let's just print these out to make sure these numbers make sense. So print U. Seems reasonable to me. We should actually plot these out to be sure, but this is already turning into a feature-length production, so let's just assume they're good and go on. Let's not do that, because if we make a mistake, it's going to be hard to find later. So let's just quickly plot it out. So let's plot plt.plot. U is going to be our x values, and count will be our y values. We'll just make it a black line. That looks good. Okay, we're good to go. So let us just, we'll keep that around. We'll just comment it out. We'll say v is equal to, this will be our random numbers. And now we're going to just interpolate to get the corresponding values of this weird probability distribution. So samples is going to be equal to np.interp. I believe this is backwards from the way MATLAB does it. So we want our values we're interpolating onto, so those are v, and then our x and y values, and now these are backwards, so it's going to be count, and I believe it is u. This always confuses me since I'm used to MATLAB, and I think this is the correct way to do it in NumPy. So it seems to run. Let's actually build a histogram of that and see that it looks similar to the ones above. So plt.hist samples bins equals, let's do 50. We'll do density is equal to true, and we will do edge color black. Edge color black. Now we have to do let's just go C for counts, B for bins, and P for patches. Yeah, we got something that looks very much like this distribution. Well, I have the cumulative function here, but it looks very much like the histogram we had before. In fact, let's plot them side by side, or on top of each other. Side by side. Oh, I chose some of the variables that we had already used. So let's just rerun the whole sheet. That's a bad choice on my part. Okay, so now let's do a subplot, and we'll plot right next to it our original SPX data. So I'm just going to copy this whole damn line, if I can get it. Copy. Paste. This is going to be SPX, or not SPX, PCT, and then we're going to need our subplot command. So let's go up here and do plt.subplot. We want one row, 2 columns, and this is the first plot. Let's come down here, plt.subplot. 1 row, 2 columns, and this is the second plot. And now this is, the title needs to be changed to SPX data. SPX data. Now let's rerun the whole sheet, and hopefully there's nothing wrong. Can we space this a little better? Oh, let's not subplot it. Let's just plot them one on top of each other. So let's just get rid of that. Oops. C, we'll get rid of this. We'll just cut that out here, paste it down here, and rerun the whole damn thing. Pretty good. They look remarkably similar to each other. So in principle, that's it. Cool. So as usual, I will clean up the notebook and upload it to GitHub. And until next time, see ya.